Welcome back, everyone, to our continued discussion of logistic regression, the theory and intuition behind the model. In part 2, we'll discuss the mathematics of converting a linear regression model to a logistic regression model. So let's go through the mathematics of converting this linear regression that we know is not going to be a good fit for categorical labels that are only 0 or 1 to a logistic regression where that curved model can actually fit those points. As a quick note, the relevant reading in ISLR is section 4.3, Logistic Regression. Now we already know the linear regression equation. We derived it before, and it's essentially y hat is equal to these beta coefficients times the relevant feature variable. And we can see that we could just describe this with terms of sigma as a sum of the coefficient times that feature x. And we also know the logistic function, and recall that the logistic function transforms any input to be between 0 and 1, which is essentially exactly what we're looking for. We're looking for something that is going to output either a 0 or 1 or something in between that range that we could then treat as a probability. So this allows us for a very easy fix. Essentially, all we need to do is plug in the linear regression equation into the logistic function to create logistic regression. So in terms of the logistic function, you could just say that y hat is equal to the sigmoid or logistic function, and then you're just passing in that sum of the coefficients times the features. And then if we write this completely fully out, so writing it out fully, it looks like this. We get y hat is equal to 1 over 1 plus e to the power of negative, and then the sum of those coefficients times the feature. And that's logistic regression. So pretty simple and straightforward. However, this does present a new question. How do we actually interpret these coefficients and their relationship to y hat? Previously with linear regression, it was really easy to see the relationship of the coefficient and then how an increase in 1 unit could be interpreted versus the coefficient and its effect on y hat. However, with the coefficient essentially being hidden or put all the way in that denominator as a power of the e, then we have an issue there that it's a nonlinear relationship. And so we have to think, how are we actually going to use things like natural logarithms in order to get a more understandable relationship between the coefficient and y hat? Because right now, it's difficult to see how we could actually interpret this being put in the denominator as this exponential of e. The first thing we need to understand in order to understand the relationship between the coefficient and the predicted output is the term odds. And this is a term that you may actually already be familiar with from gambling odds. So if you've ever gone to a casino or a racetrack and you've heard of this term, odds, you kind of already have an idea of what we're talking about here. So in gambling odds, they're often referred to in the sense of some number n to 1, or some number to another number. For example, the odds of this horse winning the race are 100 to 1, or 2 to 3, or 4 to 1, etc. But where does this number formation actually come from? Well, specifically in mathematics, the odds of an event with probability p is defined as the chance of the event happening divided by the chance of the event not happening. So it's essentially just a ratio here. It's the probability of it happening versus the probability of it not happening. So when someone says something like the ratio is 2 to 1, this is what they're referring to. The ratio of the probability of it happening versus the probability of the event not happening. So let's imagine an event with a 50% probability of occurring. So we believe that the probability of this event is 50%, so we plug it into this odds formula. So that would be 0.5 divided by 1 minus 0.5, which is equal to 0.5 divided by 0.5, which is the same as 1 over 1. So we just simply report that as a 1-to-1 odds of occurring. So that essentially reports back to the user that there is the same chance of it happening versus the same chance of it not happening. The odds are 1 to 1. Now that we understand odds, again, that's the probability of an event occurring over the probability of an event not occurring, 1 minus p, I can actually take the logistic regression formula shown here below, and we can rearrange it to show that it's equivalent to modeling the log of the odds as a linear combination of the features. So what does that actually mean in plain English? Essentially, what this is going to allow us to do is take this formula or take this equation and solve for the coefficients, that is the beta coefficients and feature x, in terms of log odds, that is the natural logarithm of the odds ratio. That way, I can more clearly see and interpret the coefficients themselves and how they relate to y hat. Because if I just try to read the equation here as it is, it's really difficult to actually have some sort of intuition or interpretation of what that beta coefficient's relationship is to my predicted output y hat. But what I could do is try to solve for just beta times x on one side of the equation and then see what the other side looks like. And we'll see later on when we actually work through the math here that it's going to be equivalent to the log odds. So let's actually solve for these log odds. We have here logistic regression, and what I want to do is essentially solve so that beta times x, that is the sum of beta times x, is on one side of the equation. That's that linear combination of the coefficients times the feature set that we're actually already familiar with linear regression. So first step is to get rid of this denominator. So I'm going to multiply both sides by that denominator, which is 1 plus e to the negative power of this sum of coefficients times features. And since y hat is on one side of the equation, we essentially now get y hat plus y hat times e to the power of negative and then the sum of the coefficient times x. So that's equal to 1. And then the next step after that is to subtract y hat from one side of the equation, or actually from both sides of the equation. So here we subtract y hat from both sides, and you can see I have 1 minus y hat, and then on the left hand side I have y hat times e to the power of this linear relationship of the coefficient times the feature set. So then what's the next step? Well, there's essentially two steps being shown here. I'm going to divide both sides by y hat, and then I can simply do the reciprocal or flip the sign here, because again you'll notice that on the left-hand side, I start with e to the power of negative, and then the sum of the beta coefficient times the feature set, which means if I reverse that sign so that it's e to the power of positive, the sum of beta coefficients times x, I just need to take the reciprocal or flip that fraction over to get that relationship. And again, now we have what is clearly looking like something in terms of odds. Notice I have y hat divided by y minus y hat, and that's the exact same thing we saw earlier with the odds. Probability divided by 1 minus probability. And we already know that in terms of the logistic regression, that y-axis that goes from 0 to 1, which is the output of y hat, I'm going to treat that as a probability of belonging to the 1 class. So I'm almost there. I just need to get rid of this e. And we know that we can get rid of an e by canceling it with the natural log, which is the log odds. And keep in mind, sometimes you'll see this written out as just log, so that essentially implies that the base of this logarithm is natural, but we'll go ahead and type it out as ln to really specify that we're talking about the natural log here with base e. And now what we see here is the log odds being equal to this linear relationship of the beta coefficient times that feature. And now we're getting somewhere where I can actually interpret these beta coefficient values. Keep in mind, it's still not direct and very intuitive, because while the right-hand side is very clear, the left-hand side is still kind of need to think about, but this is a lot easier than what we had before. So the question arises, what would the function curve look like in terms of log odds? So the left-hand side went from y hat to being in terms of log odds of y hat, where again we're treating y hat as a probability here of belonging to the 1 class, because it just goes from 0 to 1. There's two classes there, class 0, class 1, and has to be a value in between those. So if y hat is equal to 0.8, I'm saying that's a probability of 80% chance. So what I have inside that natural log are my odds, and I'm just taking the log of those odds, and that's equal to this linear combination of the coefficients times the feature on the right-hand side. So let's go ahead and convert that logistic regression that is in terms of the y-axis being in y hat to being in terms of log odds. So again, what I'm going to do here is right now I have my y-axis in terms of y hat. But if I take a look back at this, I was able to figure out this relationship in terms of log odds. So how do I actually convert this y-axis to be in terms of log odds, and what would that look like? So if I were to convert y hat to be in terms of log odds, what's going to happen is I'm essentially going to convert all the values between 0 and 1 to fall into that log odds equation. So let's consider what that mid-range value would look like. Right now I know that this sigmoid function or logistic function squeezes everything to be between 0 and 1. So that means the halfway point is going to be a probability of 0.5, a 50% probability of belonging to the 1 class. What would that look like in terms of log odds? Recall that we actually already discovered this, that it's 0.5 to 1 minus 0.5, which is the same as 1 over 1, or logs of 1 over 1, which is equal to 0. So you can get out a calculator and just plug these numbers for yourselves, but you'll realize that the natural log of 1 is equal to 0. So now, if we consider p is equal to 0.5, our halfway point in terms of log odds is now equal to 0. Then you'll realize that as you keep getting closer and closer to 1, the natural log of these odds is actually going to go to infinity. So as the probability gets closer to 1, you essentially have 1 divided by a very, very small number, and the natural log of that starts to go towards infinity. Likewise, as your probability goes to 0, then you're essentially saying 0 divided by something very close to 1, which is starting to go to negative infinity. So in terms of log odds, we actually now have the points at infinity and negative infinity, because these points that are already defined, they have set values of 0 and 1. Keep in mind, these are the actual data points that we're talking about here, not our predictions. So if we actually then convert that logistic curve to be on a log odds scale, it looks like a straight line. And the coefficients in terms are now in the change in log odds. So essentially, all I'm saying here is that if I show this equation in terms of a linear relationship between beta coefficient and the x feature, then my y-axis has to then be in terms of log odds. And because we're converting things to log odds, my y-axis goes from negative infinity to positive infinity, where the class points that are already defined are at negative infinity and positive infinity. So this is essentially transforming that squiggle, if you will, or that curve of the logistic function into a straight line. But that did come at the cost of having to transform the y-axis into log odds that go from negative infinity to positive infinity. So now that I did this, the question arises, was all this work worth it? Is the beta coefficient actually simple to interpret now? Unfortunately, the answer is still not really, but it is going to be easier than before. Because what do I have right now? Since the log odds scale is nonlinear, that means a beta coefficient value cannot be directly linked to this idea of a 1-unit increase as we could in linear regression. Recall previously in linear regression, when we were interpreting the coefficients, if I had a beta coefficient of 2, then I could say with all things being held equal, if I do a 1-unit increase in this feature, I expect an increase of 2 in the output. But that was with a direct relationship with a linear y hat. But right now, this beta coefficient is tied to the log odds. So there are some straightforward insights we can gain, but the thing to note here is that I can no longer say this kind of very simple relationship of a 1-unit increase of x results in this increase in y, because it is nonlinear due to the fact that it's not just the odds, but it's the natural log of these odds, or log odds. But what can we gain from this insight? Well, let's first think of the sign of the coefficient. If I do take a look at the sign of the coefficient, recall my halfway point in terms of log odds is occurring at the 0 of that y-axis, which means a positive beta coefficient value indicates an increase in likelihood of belonging to the 1 class with an increase associated with the x feature. So again, if my beta coefficient ends up being positive, I can say overall that if I increase the x feature, then I'm increasing the likelihood of belonging to the 1 class. I can't make a direct comparison like linear regression that I'm saying I'm increasing the likelihood by this amount, because that's going to change depending on the value of x because it's nonlinear. But I can say that a positive beta coefficient indicates that it's an increase in likelihood of belonging to the 1 class as you increase that associated x feature. Likewise, if I have a negative coefficient, that indicates a decrease in the likelihood of belonging to a 1 class with an increase in the associated x feature. So I can still actually use the sign as kind of this positive relationship versus this negative relationship between the features. Now, what about the magnitude of the coefficient? as I've said a bunch of times already, it's much harder to directly interpret the magnitude of the beta coefficient directly, especially when you could have something like a discrete x feature or a continuous x feature value. What we can do, however, is begin to use the idea of an odds ratio, essentially comparing one set of odds magnitude to another set of odds magnitude. And to put that simply, it's just comparing the coefficients to each other. So if you compare the magnitudes of the coefficients against each other, it can lead to insight over which features have the strongest effect on prediction output, especially if you've already scaled your data so that you have a standardized or normalized set of x features. If you have one feature with a really large positive beta coefficient and another feature with a very small positive coefficient, you can directly compare those magnitudes and say that the feature with that very large positive coefficient is a much stronger predictor of the likelihood of belonging to class number 1 than the other feature with a very small beta coefficient. Again, you can't directly then say that a 1 unit increase results in this increase in y, but you can then compare the magnitudes in order to see what features are more important than others, or what features have very strong predictive power. So the last mathematical topic we need to discuss concerning logistic regression is how we actually fit this curve. You'll notice here I have 3 different logistic regression function calls, and they are actually all, in a sense, fitting to these points, but which one is fitting the best? We'll actually discuss the basics of fitting the best logistic regression curve with something called maximum likelihood in the next lecture. Previously, we fit using residual sum of squares, but we can't actually use that for logistic regression. We'll need to switch gears and discuss maximum likelihood, which is good because maximum likelihood is actually used in many other machine learning algorithms. So I'll see you at the next lecture where we begin to discuss how we actually find this best fitting logistic regression curve. I'll see you at the next lecture.